Recording now. All right, so we have a question in the Discord chat about whether or not code blocks needs to be the 64-bit one or the 32-bit one. It basically depends on what operating system you have. If you're running a 32-bit operating system, you must have 32. If you're running a 64-bit operating system, you should be able to use either 32 or 64-bit. So it does depend on your system's configuration. 32 will work on either though, and we don't do anything that requires 64 bits. So I would, in case of you're not sure, just go with 32 bits. All right, so I'm going to start sharing the screen, and we'll continue with the theory. And then for those of you who are eager to get started with your practical assignments and start getting into the coding side of things, remember that in today's tutorial, we will cover everything you need for practical 1 and then the following week's practical 2. So we'll continue with the theory right now. All right, I've started sharing. It should come through now. Okay, and it is recording, so we should be good to go. So let's continue with the theory. So we discussed the basic idea of binary numbers, and we discussed the fact that binary numbers can be converted from binary into base 10 very easily by using the fact that it's a positional numbering system and raising the value of each digit multiplied by the base of the numbering system raised to the power of the position. And remember that because our least significant bit is in the rightmost column, that's 2 to the 0, or position, that's 2 to the 0, then 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4, going from right to left. All right, I won't be able to respond to up hands or anything because we've been told to keep the chat off in these sessions by management, and until they tell us to do something else, we will have to continue to do that. However, they didn't say we couldn't have Discord running, so I will check Discord periodically, but I will need to continue with the work, so I'll only be able to check it periodically throughout the lecture. All right. Okay, so that was the one thing we covered. Then we covered the algorithm for converting in the opposite direction. And we saw that we used multiplication in essence to go from binary to decimal. Exponentiation is really just another kind of multiplication. So what's the inverse operation of multiplication? It's division. And of that, there are many kinds of division. We had integer division, we have modulo division, and you have real division. So integer division will get you the dividend, but will throw away any fractional components. And modulo division will give you the remainder that you would have gotten had you done integer division and not thrown away the remainder. So by using both of them, you can repeatedly use integer division by 2 to convert the decimal number and bring it down to 0. And you just record the remainder at each step, and then you read the number from bottom upwards to get its binary representation. We then saw that there were logical operations that are built on top of binary representations, with the number 1 representing truth and the number 0 representing falsehood. And the fundamental binary operators are known as not, and, or, and exclusive or. And we discussed how they work on a binary level, where they basically operate on individual bits in the case of not, or pairs of bits in the case of and, or, and XOR. And we will discuss, there's some nice things you can do with these things. Actually, let's do an example with it. So for example, XOR, or XOR as it's sometimes known as, is used to perform the world's simplest form of encryption. Well, not actually the world's simplest form of encryption. As you'll see, there are other algorithms that are also quite easy to do, which we might do as practicals or examples with you. But bitwise, XOR works very well, in the sense that it's easy to do, but it's not very secure, so it's not used in practice anymore. But I will discuss it. It's not as insecure as people think. So what is encryption, firstly, in case you don't know? It's where we take a message and we convert it using an algorithm. So remember, an algorithm is a series of steps that we need to transform some value into another value. It's an algorithm for converting a message you want to send into a obfuscated, altered version that is difficult to understand. And then there should be a reverse process which will decrypt it and convert it back into the original. So it allows for secret messages to be sent. And they've been used since antiquity, obviously getting more sophisticated as time goes forward. XOR works very well on binary representations, and we'll explain now. So let's imagine the message that we wanted to send was this number, whatever that number may mean. Could be an account number, could be interpreted as characters, could be lots of things, who knows, doesn't really matter. And we wanted to encrypt it. So encryption algorithms often have some form of encryption key, which is sort of like the password that you're using to perform the conversion. So in our case, for XOR, our key will just be any other binary number. I'll label that as K for key. If you are doing XOR encryption for what it's worth, it's often used as an example of a very simple, easy to defeat form of encryption. And for sure, there are definitely better ones these days. But for what it's worth, if your key length is the same length as your message length, then it is impossible to break the encryption. The downside is, of course, that your key has to be as long as your message. So it's not really efficient. And as you'll learn if you do go into the security field, that the issue of how do you get your key safely to someone else so that they can encrypt messages to send to you, if you don't trust the communication mechanism you're using to send the key, is a whole other problem, which this does not solve. But this isn't a security lecture. It's simply a lecture on binary and on logical operators. And this is simply showing you one use of the binary numbers and logical operators to do a simple encryption. So if we wanted to encrypt this message M with this key K, we simply perform the XOR operation between the two. So remember, XOR's rule was if the corresponding bits are different, we get a 1. If they're the same, we get a 0. So as I said, I like to think of it as the new South Africa operator. It loves diversity, so it's happy, gives a 1 when things are different, and it's sad, gives a 0 when results when the inputs are the same. That's just the mnemonic that I've always used to remember it. So in any case, here we have 1 and 1, they're the same, that's 0. 0 and 0 are the same, that's a 0. 1 and 0 are different, that's a 1. 1 and 1 are the same, that's a 0. And 0 and 0 are the same, that's a 0. So this is our encrypted version of the message, which we could safely send over the internet or whatever, and to our recipient, who presumably we've already secretly delivered the key to. And let's say that on the other end of the communication, they wanted to reverse this process and read the original message. They could easily do that. They've got the key. They simply perform the same operation again. So 0 and 1, different, gives us a 1. 0 and 0 is the same, gives us a 0. 1 and 0 is different, gives us a 1. 0 and 1 is different, gives us a 1. And 0 and 0 is the same, gives us a 0. And you can see we've gotten back to our original message M. We've reversed the process. So provided you can distribute the key securely, and provided that the key is the same length as your message, this is an unbreakable mechanism, because literally any possible pattern would result. It would all depend on what your key was in the original. So that's an example of a use of the XOR logical operators. I'm just going to quickly skim and see if there's any questions. Oh, you can't see my screen. That's weird, because it seems to be sharing over here. I'm seeing the stream coming through. I'm not sure if that's an old message. All right, and then when it comes to binary to decimal conversion, are we always given the base, like base 2 and base 10? Yeah, no, I'm not going to make you guess, because there's no way that you can tell if you saw 101, if that's 101, or if it's 101 in binary, or if there's even octal or hexadecimal, they could be the number in. So I'll always tell you what the base is, either with a subscript, or I'll tell you in the question the number is in base 2 converted into base 10 or something like that. So if the key is not the same length as the message, it's a good question. Then the number of possible patterns that could result from this approach isn't infinite, well, not infinite, but isn't the same as the number of all possible patterns that could fit into that length. So it's less secure, but obviously any key that's close to the length of the message will be pretty secure. But sometimes people are really lazy when they do XOR encryption, and they just use a single digit as the key, or a single character. They sometimes do it on a character basis. So that's a character, for what it's worth, is about 8 bits long, and that's not secure at all, because then all you'd need to do is to try all the possible permutations, scan the resulting data to see if you can detect anything, like put it through a dictionary test to see if any words pop up or whatever, and then you'll find very quickly what it was, assuming you had some sense of what kind of data it was. If you knew it was text or something, you could look for something in the resulting output to see if you got it right. No, I can't do anything about the annoying beep sound in the background. I'm currently being load shed. It's my UPS. So if it weren't on, there'd be no connectivity, unfortunately. That is part of the world we currently live in, unfortunately. So what you can do is exercise your right to vote and agitate for the building of better power infrastructure and the building of more power stations, particularly renewable ones. So if that is an important issue to you, then it'll be important to the politicians. It's not going to ever be important to them if it's not important to you. All right, so let's continue. All right, so the different operators have different precedence levels. So what's a precedence level? It's basically which ones get applied first. So it's the same as in mathematics, where you have the precedence table, which you might have learned as BEDMAS or BODMAS or PEMDAS or PEM. There's variations of them, but it's basically the same. So you can think of not, if you want to think of them as equivalent to normal arithmetic levels of precedence, not has about the same level of precedence as exponentiation, and has the same level of precedence as multiplication, and OR and XOR have about the same level of precedence as addition. But if there's any ambiguity between the two, then apply the XORs first, for what it's worth. You can also distribute the logical operators and values like you would in mathematics. It's very similar, with one small difference that's fairly important. So just imagine the ORs are pluses, and then you can happily move the brackets around quite easily without needing to think too hard. Likewise, think that the ANDs are multiplications and the ORs are pluses. So the rules are the same for distributing into brackets. And then commutative, doesn't matter the order in which they're applied. They're going to give the same results, provided that there's no brackets or anything else in play. The one thing that is different, however, is the rule that goes with logical negation. Because what you can distribute a not into brackets, but you then have to flip the ORs to ANDs and the ANDs to ORs. We won't worry about XORs, but for ANDs and ORs, the law is called De Morgan's law, and you distribute in, but then the OR becomes an AND, or the AND becomes an OR. And it's very easy to forget to do that in your mind, because we'll use these logical rules when we're writing code to come up with logical tests for various conditions. And it's very easy to forget about De Morgan's law, and you negate something, but you forget that it affects the AND or OR as well in your reasoning. So it is something to just bear in mind. All right, so with these logical gates, they're actually how the chips and circuits are implemented in electronic devices. So you can combine these circuits to do anything, including things like addition, subtraction, multiplication, or much more sophisticated operations. And these are basically combined into logical circuits, which look as follows. So, okay, sorry, this is blocking the view, but the inputs flow in. We're using this particular notation for OR gates, AND gates, exclusive OR gates, and NOT gates. There are other notations which just use the circle for knots, but we're using the inverter notation for what it's worth. So if you're doing electrotechnics, I think they might use the other notation, but this is the one we use. Just bear that in mind. So you can represent a Boolean expression and convert it into a circuit that will then do the same thing that that this logical expression does. So each of these individual logical operators is implemented using a very small electrical device called a logical gate. And by combining these gates together, we're able to create the circuits that we're interested in. For what it's worth these days as well, they now actually have hardware where you can rearrange the circuits with magnetic fields. It's called field programmable gate arrays. So you can basically have hardware that can be updated with a download or software. So I still think that that will become increasingly more important going forward. It's still a bit expensive these days. So yeah, that's that. So you can get questions in your theory tests where you get given an expression like this and you have to draw the corresponding diagram. So the important thing is to take into consideration the brackets. So we know that these ORs need to be applied first. So A and B go into that OR gate and C and D go into that OR gate. We then know that the NOT needs to be applied. And we then know that they all feed into a single AND gate to give you your final result. There's actually supposed to be a space between those. They just got too close in the editor so that they appear as one, but it's actually two single inputs into that AND gate there. So binary addition, basically, as soon as you reach a what would have been 2, you roll over to 0 and carry 1 to the next most significant position, just like you would in arithmetic. So if you are writing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, in binary, it'll just go 0, 1, and then 1, 0, and then 1, 1, and then 1, 0, 0, and then 1, 0, 1. But we'll do an easier way of doing binary counting now. So just if for what it's worth, the rule is the same. You just don't get up to even 2 before you need to roll over and increase the number of positions. All right, let's continue. Okay, so there's faster ways of doing it than obviously how a human would do it, using XORs to work out the outputs and ANDs to determine the carry bit. And then there's a little bit more complicated than that. You basically create these large circuits known as half adders, and you combine 2 of them together to form full adders. It's because we need to get going with the programming, we never really focus on those details. We just worry that you know that the circuits exist and that they can be combined and that they represent Boolean operators, and that you personally can do binary conversions more than manipulations we worry about. But just for what it's worth, how would multiplication potentially work? You could just do repeated addition to do multiplication, or they might come up with more sophisticated circuits that can do it quicker. But the point is that multiplication is pretty much always, except in some edge cases, a much slower operation than addition and subtraction, because it's often a repeated application of a lower level instruction. For what it's worth, there are simple cases, which we'll discuss. I can actually do it now, actually. So let's go. We've got 1, 0, 0, and we've got 0, 1, 0. So what is 0, 1, 0? We can see that that is 2 to the 0. Ignore that. It's just 1, 2 to the 1. So we know that that's 2. And we can see that this over here is, well, there's no 2 to the 0s. There's no 2 to the 1s. There's just a 2 to the 2. So we can see that that is 4. So let's say we added extra zeros to the other side. That doesn't affect the final value. What would 1, 0, 0, 0 be? Well, you can guess that it's going to be 8. And you can see that shifting a binary number to the left or to the right either multiplies or divides it by 2. So computers often have optimizations where they'll detect easy cases, things like multiplying by a power of 2, and convert it into a series of shifts rather than actually doing the multiplication. Or obviously things like multiplication by 0 are trivial. You just zero all of the outputs and get the correct results. So Computers do try and minimize the work, but some operations like multiplication and division, particularly as we'll see when you have real numbers involved, can get very, very complicated and expensive. So the computers do them much more slowly. Okay, so we have special names for collections of bits. So a single binary digit, as we said, is a bit, 1 or a 0. And we often group them into groups of 8, which is traditionally called a byte, although technically speaking, different computer systems have had different numbers of bits in a byte. 8 is the most common, but you have had 6 and 7-bit bytes and other strange variants. So if you ever need to talk about it in a completely neutral sense, the correct term is octet. So when you do computer science 2B and you learn about internet protocols, you'll see that because internet data needs to be sent between completely different kinds of computers, they'll refer to that as an octet or an octet stream rather than a byte stream, technically speaking. It's very rarely used, but the term for half a byte is a nibble with a Y. I think they made that more as a joke because you don't often really work in 4 bits. But I guess the term does exist. It's a real term. And then, as I said, every computer architecture has a specified number of bits, and that's the word size for the architecture. So I don't know if you're into computer gaming, you would have been very aware of it, that there were these different errors in the evolution of computer gaming based on the number of bits that were in the word sizes for those early entertainment systems, the 8-bit era, and then 16-bit, and then 32, and now we're basically in the 64-bit era. And there's no real compelling reason to shift over to 128-bit hardware, although some of it does exist, because the real gains don't come from just having more bits in your word size. So 64 seems to kind of be the sweet spot, but who knows? Who knows what will happen? And there's several impacts that happen based on the size of the word size and the number of bits that you've got available to you. Basically, it influences how accurate your results can be and how big the range of values can be. If you're dealing with just literal whole numbers, then obviously accuracy isn't so much an issue, except for the fact that you can only represent a finite number of numbers. But if we're dealing with real numbers, then the number of bits that you have available improves the accuracy of your values. So we'll just discuss now how to represent negative values in binary. So notice there's only 2 real symbols that exist. In binary. There's 1 and 0. So how could I represent a negative number? Well, if I have a minus sign, I'm introducing a new kind of value. We discussed that the whole point of computing with 1s and 0s was that you only have 2 possible states because it's easy to register the presence or absence of something. So if we suddenly got a new intermediate value to represent a negative, then that's an issue. All right. Okay, so none of those I'll address at the moment. Will you need to know which direction the data flows through the logical circuits? The assumption is that it flows from the inputs. So you'll be given the variables, A, B, C, or D. Those are the inputs into the system. So it flows from them. There's no difference in meaning. There's no up or down, but it's from the A, B, C, and D inputs into the circuit. That's we won't ever give you something like with a short circuit where there's a cycle or something like that, because that wouldn't work electrically, at least not for the purpose of creating logical circuits. So that's a good question. And then, yeah, there are various techniques for counting to relatively high numbers in binary on your fingers. I know of them. I can't say I use them. Are the notes for the practical or only the theory? That's a good question. Your first test is a theory test, remember, and that's in less than a month now. But knowing things like the impact of representing numbers and how negative numbers are represented and how real numbers are represented has a very real impact on your programming, because some kinds of errors are introduced if you don't know how numbers are represented at the binary level. And these errors have been very costly. They've done things like crash spaceships and caused disasters because people didn't realize that you can't fit an infinite amount of data into a 64-bit word, for example, and then what happens when you try and squeeze too much data in as well. We will show you, and then you'll see it in practice in the code as well. So that's part of the reason to do something like C++, which is both very high level and very low level, so you can understand both ends of the programming equation. So if we're representing negative numbers, we need another symbol. So one technique, which is the laziest technique, is to just add an extra bit, and that bit's either 0 or 1, and it basically just represents 1 or 0, plus or minus. So 0 if it's positive and 1 if it's negative. It's not great, because what happens then is if you do addition, you have to have special circuits that check for the sign bits, and then they will do different operations depending on whether the sign bit is 1 or 0. So it means more complicated circuitry, which means either the stuff takes longer or is more expensive. It also means that they produce more heat. So there's a lot of reasons that we don't actually use sign and magnitude as our system. The system we do actually use is one called 2's complement. So I'll discuss the mechanism for doing it before we go into the rationale of it. And you don't really need to understand the rationale of it too deeply. So don't worry, if you can do it, we're happy, rather than necessarily the why, but I will discuss the why. So let's say you wanted to represent a negative number. Sorry, that shouldn't be a superscript, that should be a subscript. That's a very big number. So 29 to the base 10. First thing you do is obviously you convert that number into binary, and then you logically negate it. So technically the logical negation of the number is called the 1's complement of that number. And then you simply add 1 to it, and then you have your final result in 2's complement. The joy of 2's complement is that you can use the same circuits for addition and subtraction, because adding the 2's complemented version of a negative number to a positive number will have the same result as subtracting the positive version of that number. So that's a very desirable characteristic. It doesn't require you to have separate circuitry to handle addition and subtraction, and it doesn't require you to have special cases for checking the sign bit. And also, yeah, so that's very useful. So a question for the designs for practicals can absolutely be handwritten and uploaded with CamScanner, no problem whatsoever. We'll go through the designs during the tutorial as well today. All right, so let's continue. So, okay, in brief, because you're not going to get this in the theory test anyway. Why do we have these why do we have this 2's complement system? What does it basically mean? Well, think about the number 0. What does the number 0 actually mean? There's nothing special about the number 0. It's just the boundary point. Well, there are things that are special about it. It's the only number that's, neither positive nor negative. So that is special. But it is not magic in that sense. So it's just the boundary between the positive and negative numbers. So you could pick a different boundary between the positive and negative numbers. So let's say you were representing values with 4. Let's just stick to base 10. You had 4 bits. You were representing, or 4 base 10 numbers. You're representing values from 000 up to 999. You could pick 500 as being 5,000 in this case. Sorry, 5,000 as being your new 0, your halfway point. And then you treat numbers that are less than it as negative and numbers that are greater than it as positive. So you split the range of your numbers into 2 halves. So the magnitude, the absolute magnitude you can represent is now half, but you can represent positive numbers and negative numbers. The issue is, when you do something like that, is you actually have 2 valid representations for the number 0. You have positive 0 and negative 0, effectively. This would be positive 0, and this would be negative 0. And this is actually a thing that does happen in computers. You might sometimes see negative 0 appearing or positive 0 appearing. So the fix for this, or the issue that gets introduced, is when you've got something crossing that boundary, it's off by 1. And you just need to adjust that by adding the 1 back to it. So that's effectively what this long discussion means. You create a complement operator, which allows you to convert to and from the positive and negative representation. The properties of this complement operator should be that if you complement twice, you get back to the original. So basically, in the base 10 example, your complementing is simply shifting it with 499. And then, so that gives you the tens complement 1. We discussed the issue of the being off by 1. So sorry, that's the nines complement version. However, you can adjust it into being the tens complement version by dealing with the off by 1 error. So that's in base 10 how it works, and then base 2 is how the computer actually works. So that's all we care about, and it's really easy. It's simply not the convert into binary, apply not, add 1, and you're done. We will practice these in the lead up to the semester test. All right, so here's an issue, binary fractions. So let's say we have a number with like a decimal number, 123.456. So what does 3 represent? That represents groups of 10 to the 0. What does that represent? Groups of 10 to the 1. What does that represent? Groups of 10 to the 2, and so on and so forth. So if we're going backwards, if that was 10 to the 0, what would this be? That would be 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. So basically tenths, hundredths, units, negative units, tenths, hundreds, thousandths, and so on and so forth. So that's the same idea in binary. You could definitely do that. And this would be units, this would be twos, so this would be halves, this would be quarters, this would be eighths, this would be sixteenths, this would be 32ths, and so on and so forth. So you could represent your number, but it wouldn't be precise because there are some fractions that you can't really get to nicely by adding combinations of halves, quarters, eighths, sixteenths, 32ths, 64ths, 128ths, and so on and so forth. It'll be close, but not exact. You might say, oh, well, that's terrible, binary's bad. But the same is true in decimals, just different numbers that have these properties. For example, if I have a third, what is that in decimal? That's 0.3 recurring, because we can't nicely represent this in base 10 as a fraction. Same story with binary. You'll have these recurring binary fractions that'll get you arbitrarily close to the exact value, but not precisely close. It's important to note, of course, that 0.3, well, that things like that introduces some edge cases, which we'll discuss in programming, even in base 10. So for example, 0.9 recurring off to infinity, not just a fixed number, is exactly the same number as 1. There is no difference between those two numbers. They are precisely 100% the same number. And you might say, no, 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 it's off by some very small amounts. It's not. These are exactly the same number. If you disagree, let me just show you very quickly. What is a third? We said it's 0.3 recurring. So I ask you, what is a third plus a third plus a third? You're going to tell me it's equal to 1, isn't it? Right? So then if I tell you what is a third, 0.3 recurring plus 0.3 recurring plus 0.3 recurring, it's going to be 0.9 recurring. So I'm sure you will agree that 1 is equal to 0.9 recurring. Right? Well, a third plus a third plus a third gives me 1. 1 over 3 in as a decimal fraction is 0.3 recurring. A third plus a third plus a third gives me 1. Oh, this is just a different representation of 1. They are the same number. All right, let's just see if there's any other questions. All right. No, the weird beeping noise I said before, please listen, is the fact that I'm currently undergoing load shedding. So there's no way to get around that. All right, yeah, we'll discuss the difference between signed and unsigned ints, but the fact is that under the hood, they use these techniques. So an unsigned int is under the hood using 2's complement. That's the mechanism that's used to represent it. Do you need to know the unary and Roman number systems? It could be asked in the theory test. You don't need to know how to do operations with them. You just need to know what they are. So it'll be a quick throwaway short question. You're never going to be asked to do a calculation or anything. All right, oh, sorry, I see you've gotten to the UPS bit. All right, back to, I think we're out of time now. We know we've still got a few more minutes. So let's keep going. So, okay, yeah, so I've discussed the issues that can be occurring with binary fractions not being precise, but no finite numbering system is perfect. So, it's going to happen in other numbering systems just for different things. But it is a real issue. You can never squeeze an infinite amount of data into a finite amount of space. So other very useful numbering systems that exist are hexadecimal, which have the character 0 to 9 followed by A to F. You can do conversion by decimal using the same technique that we discussed for binary conversion if you want to, but it's silly. We'll show you a better way now. And obviously, if you can write fun words in it because it's got some letters in it. So they actually use hexadecimal fairly frequently to write special values in binary files so that you can see where the beginning and end of certain sections in the file is. So for example, all Java files will start with the binary representation for, I think it's Cafe Babe. All of the Java class files will have that as their binary value, and various other cutesy patterns that people write with binary numbers. Just so that if you're inspecting the file in binary, you can see, that's that section beginning, without having to open it in a special editor or anything. All right, so we'll learn now, and then there's octal, which uses 0 to 7 as its symbols, and both of these are effectively used as shorthand for for binary. So let me now quickly show you the one easy way for doing binary conversion. And if we end off on that, that's actually fine, because that's where we need to get to. How do I do conversion from binary to hexadecimal to very small decimal numbers very, very easily? The way you do it is you simply write out a sequence of 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, followed by 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. Actually, I hope I didn't miscount. Then you follow that up with a sequence of 4 zeros. 1, 2, 3, 4, followed by 4 ones. 1, 2, 3, 4, followed by 4 zeros. 1, 2, 3, 4, followed by 4 ones. 1, 2, 3, 4. Oh, that's good. All right, then in the next column, I'm sure you can see the pattern. That's 2 zeros, followed by 2 ones, followed by 2 zeros, followed by 2 ones, followed by 2 zeros, followed by 2 ones, followed by 2 zeros, followed by 2 ones. And then in the final column, I'm sure you can get it. It's simply alternating zeros and ones, 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 zeros and ones. That's counting in binary, if you ever wondered. And then you can simply write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we've run out. There's no 9 anymore. There's no 10, but it's A, B, C, D, E, and F. And this will let you do binary to hexadecimal or octal conversion ridiculously easily. So let's just use this table. So if you can write that table out, you're good as gold. All right, so let's say we wanted to do, I don't know, dead in binary. How would we do that? We simply look up the corresponding letters, 1101, E, 1110, F, A, sorry, next, that's 1010, and B, we said was 1101. This number, but you can leave the spaces in it because it is easier to read, is the binary version of that hexadecimal value. Saw how easy it was to convert. Let's convert some random binary number into hexadecimal. How do we do it? We group into groups of 4. Let's actually make it so that it's not an even group of 4, just to keep our lives interesting. Okay, fine. Group of 4, pad with zeros. There's nothing wrong with adding zeros to the left-hand side of a number. It's not going to change its value. And then we simply look it up on the table. It's going to give us 0, 1, 1. That's 3. 1, 0, 1, 0 we saw was 10, so that's A, and 1001 is 9. So that is the conversion from binary to hexadecimal, really, really easily. For octal, it's exactly the same, except you only use this portion of the table. So let's say we wanted to convert 1, 1, 2, or 1, 2, 3 from octal into binary. That's going to be 0, 0. Then you only use groups of 3. That's the one difference. 0, 0, 1, 0, 1, 0, and 0, 1, 1. Just look it up on the table. And then in reverse, if we wanted to convert from binary to octal, just group into groups of 3, add with zeros if you need to on the other side, and look it up. So 1, 1, 1, see there, that is 7. The 1, 0, 1, we will see as 5. And the 0, 1, 0, we'll see as 2. So that's conversion from binary to octal very easily. So you can see why people use this. They use it because it is super quick. So basically, you can use binary value, you can use hexadecimal and octal as a way to summarize binary data really easily. You can see this is much shorter than that long sequence. So that's why it's used in computing. And then we can just quickly look at these other things, but there's not much really we need to do. There are other ways to represent binary values, decimal values using binary. There's one called binary coded decimal, where you simply use the same lookup table, but with the decimal number and convert it into binary. It's not very efficient. You can see here that if I use proper binary, and I've got, let's say, 32 bits, I can represent 4 billion different numbers, but I can only represent 100 million binary coded decimal numbers. And the bigger the number of bits gets, the less efficient binary coded decimal is. So we don't use that. And then there's packed binary coded decimal, which basically they just use the first group to represent plus or minus. So it's a different way of doing positive and negative. You don't have to really worry about these. We won't ask you to do them. And then you can work through that in your own time. So perform your own tests. So that's that, ladies and gentlemen. Are these notes in the textbook? No, but they're on Eve. So you should be accessing Eve to retrieve your lecture slides. So Eve, just as a reminder, you access it. This is the course management system that we use. You log in initially with your student number, username and password. You can see then obviously then as a real user, please change your password, but don't forget it. And then you can see your lecture your lectures themselves. Under here, Computer Science 1, and you can see there's the lecture notes on numeracy, and there you have them. And plus this lecture slide will be uploaded to Eve as well. And then just because we've got a moment left, I think, let's see. All right, if you're watching this late, your password is ENG137 to access to record that you've watched this on the link for YouTube. All right, so I think that's it. It's about to disconnect me because we're about to run out of time. I will be starting the tutorial soon, and we'll be doing some C++ work in that. So you can connect to me there if you need anything more. See you in the next session if you're going to be there. If not, have a good evening. Goodbye.